नमस्ते बच्चों, हमेशा खुश रहो बच्चों। Myself सेल्फ ओम प्रकाश केसरी, फैकल्टी ऑफ डिपार्टमेंट ऑफ साइंस एंड टेक्नोलॉजी अंडर फैकल्टी ऑफ एजुकेशन एंड मैथोलॉजी. Today I taught you topology on R, in which in your last class I will see the connectedness, compactness of a topology in R square. That means two-dimensional. In your last class, I will see the Henny-Borel theorem, which state that every closed and bounded set R square is compact, which shows that every closed and bounded set R square is compact. As in R, we have the following results. The first one is the every finite set is compact. That means if any set is finite, it must be compact. Next, R square is not compact since minus n to n of R whole square. Uh, that means in and two-dimensional, where n belongs to n is a cover of R square, which has no finite subcover, because I already defined these things. That means a set in R square is compact if every open cover has a finite subcover. Every open cover has a finite subcover. And the next one is the Cartesian product of 2-point set. That means AB of closed interval AB Cartesian CD is compact. And the completeness, for the completeness, connectedness, for the connectedness, we first define the disconnectedness, and then we say that a non-empty set is called connected if it is not disconnected. Or simply we can say, when we take any 2 points on a set and match these 2 points, the all point lies in this line must be inside that set, then the set is said to be connected, and this is valid for all points inside that set. A non-empty set K in R square is disconnected. A non-empty set K in R square is disconnected if there exist open sets G and H. There exist open set G and H of R square such that K equals to K intersection G union K intersection H, or we can say K intersection G intersection K intersection H equal to phi. K intersection G intersection of K intersection H is equals to phi. And a non-empty set is called connected if it is not disconnected. Simply, that means any set is connected, then the complement of that set is disconnected, and every set is disconnected, then the complement of that set is connected. The connected set in R square is called a region. The connected set in R square is called a region, and a non-empty set K is said to be locally connected if every neighborhood of a point of R square has a connected neighborhood. Has a connected neighborhood. Now let us see one example on that. The open unit disk is connected. The open unit disk is connected, and hence is a region also. Now you can see here, if we take any point inside this disk and connect these 2 points, the all points lies inside that disk. That's why this is connected. A set K, for example, we can construct a set K equals to xy, which belongs to R square, such that x varies from -1 to 1 and y also varies from -1 to 1. Union xy, union of xy belongs to R square, such that x varies from 2 to 3 and y varies from -1 to 1, is disconnected. Hence is disconnected because the open set G equals to xy belongs to R square. Xy belongs to R square such that x is less than 3 by 2. X must be less than 3 by 2, and hence H equals to xy belongs to R square where x greater than 3 by 2. Satisfy the requirement K equals to K intersection G union K intersection H, and K intersection G intersection K intersection H equals to 0. Hence the set is disconnected. The set as equals to xy such that x square plus y square less than 1 union xy such that x minus 2 whole square plus y minus y square less than 1 is also disconnected, since the set U, which is nothing but xy, the circle xy such that x less than 1, and the V is the circle xy such that x greater than 1 satisfy the requirement for disconnectedness. These examples are shown pictorially as the circle, first one, that means open disk, and that one is the example of K, and that one is the example of S. Now we are going to move on continuous function and homomorphism in R square. A function f a function f from R square to R square is called continuous if the inverse image of any open disk is open in R square. If the inverse image of any open disk is open in R square, that means when we construct a set f from R to R square to R square, from R square to R square, and we say that this function is continuous if the inverse image, that means inverse image of this one, this open disk of any open disk, the inverse image of any open disk is open in R square, is open in R square. That means inverse disk of as delta AB, as delta AB, delta because of the arbitrariness, because of the arbitrariness. For example, let us consider the function f of xy equals to twice y plus 1 and thrice x minus 1, which is a continuous. How can we say? Let us consider the sphere as delta AB and find the f inverse equals to xy such that twice y plus 1 minus a, twice y plus 1 minus a ka whole square plus thrice x minus 1 minus b ka whole square, because the point of AB less than del square, which is equals to xy such that 9 x minus 1 plus b by 3 ka whole square plus 4 into y minus a minus 1 by 2 ka whole square, which is less than del square. And then after simplifying all these things, we got this is equals to xy such that x minus 1 plus b, x minus 1 plus b by 3 ka whole square by del square by 9, by del square by 9, because we will divide it with del square, and by 9 multiplying and dividing, and here also multiplying and dividing. That's why we will got here 1. That means dividing del square in both sides. Therefore, it is an open set, and in fact an open ellipse, an elliptic region without its boundary. Now the next definition is the homomorphism. This is the definition of continuity, that means continuous function. when we say that the function is said to be homomorphic. A bijective, which we already discussed in R. We will define it in R square also. Now a bijective function, and that place also bijective function from f from a function R to R, but here from R square to R square. That means a bijective function f from R square to R square is called a homomorphism if f is bicontinuous. F is bicontinuous. That means both f and f inverse are continuous. Both f and f inverse are continuous. And the above example of a continuous function is in fact a homomorphism also. And some notable points are there. The first one is the continuous image of a compact set is compact and hence closed and bounded. The continuous image of a compact set is compact and hence closed and bounded, which we already discussed that any closed and bounded set is compact. Now next one is the continuous image of a connected set is connected. That means if image are continuous, then it is connected. Of a connected set is connected. If D be a dense set in R square, if D be a dense set in R square, then every uniformly continuous function from D to R square can be extended in a unique way of R square. Extended in a unique way of R square. Is extended in a unique way to R square. From this one, this is the finish of topology on R and R square. Now I will see in your next class matrix space and see some properties of topology in matrix space. Now this session is powered by the digital version 2.0 JAYOTI Vidyapeeth Women's University Jaipur, and I hope all of you are satisfied with my digital session. If you have any queries, please mention in the comment box. I will try to resolve it. Thank you for watching my this lecture video. Thank you बच्चों.